All right, guys. Today we're going to deal with thermochemistry. We're going to be dealing with some vapor pressure questions. All right. We have a chart over here to the right. It says, "What's the vapor pressure of ether at 40 degrees centigrade?" Okay, so we look at our graph and we find ether, which is here, which is this line, right? Because it says right there it's ether, right? It says, "What's the vapor pressure of ether at 40 degrees Celsius?" So we find 40 degrees Celsius. We come up here for ether, and we go all the way up here. So it's about 900 millimeters of mercury. Okay, now for just a second, let's look at this chart. Let's stop and just look at the chart. Notice that here we have about 760 millimeters of mercury, and that is what atmospheric pressure is. Okay, down at sea level. So that's helpful, right? What's the normal boiling point of water? Well, it's going to be on this line. Now I have to look for water. Water's this third curve over here. So we see where it crosses this line, and where it crosses this line is at 100 degrees Celsius, which is what we would expect, right? So that's kind of how you read the graph. Graph isn't rocket science. You should be able to read the graph. Well, what's the normal boiling point of benzene? Benzene is different. It's not water. It has a different boiling point. So if I come over here and I look at benzene, and I also go up to 760 millimeters of mercury, I find that that is approximately 80 degrees Celsius. And so you should be able to read a graph like this one. All right. How's the average kinetic energy of water molecules affected when you pour hot water from a kettle into cups at the same temperature as the water? Well, if you've got water and you put it into a cup that's the same temperature, does the temperature of the water change? No, the temperature of the water doesn't change. Okay, does the temperature of the mug or the cup change? No, it does not. So it's not affected at all. It has no effect at all. Now, what happens if the cup is colder? Well, typically, when we're pouring hot water into something, the cup is colder. So at that point, the molecules, the average kinetic energy of the water goes down, and the average kinetic energy of the molecules in the cup goes up. Okay, but in this particular case, because of the way the question is phrased, it has no effect. What's the relationship between atmospheric pressure and altitude? Well, we showed you a lot of pictures where we had something this, and we had the molecules of air really tightly spaced here, and kind of not so tightly spaced here, and then very far apart there. Okay, the higher you go, the less atmospheric pressure you have. Okay, and if you have the less atmospheric pressure, remember that the boiling point of water is where the atmospheric pressure and the vapor pressure are the same. So if you have less atmospheric pressure, then you have to have less vapor pressure, which means for the boiling point goes down. So at sea level, water might boil at 100 degrees Celsius. But up here, remember, we talked about Woodland Park, Colorado, it boils at about 93 degrees Celsius. And on top of Mount Everest, it's going to boil in the 80 degrees Celsius. I don't remember, 80-something degrees Celsius. So the further up you go, the lower the boiling point. Right, vapor pressure. Vapor pressure, remember, we showed a picture of a water bottle. And the water bottle had some water in it. Let's put the water level there. Right, we have some water evaporating, and we also have water, gas particles condensing. Right, so vapor pressure is the pressure that the water in here exerts on the container after it has had a chance to reach equilibrium. Now what happens is some of the molecules are evaporating, some of the molecules are recondensing, and that becomes an equilibrium, meaning the same number are going up as are coming down. Okay, so vapor pressure is the pressure exerted by these molecules inside here that are in fact water. The water molecules that are in the air that are above the water. Okay. What's the full definition of a boiling point of a liquid? Well, the easiest thing to remember is that the boiling point is where the vapor pressure of the water is equal to the atmospheric pressure of the water. Okay, so typically that's going to be 760 millimeters of mercury, and the vapor pressure is also 760 millimeters of mercury for the water. But this can happen at a lower temperature if the atmospheric pressure is less, like when you're on top of a mountain. Right, and that's what we just said here, is that the boiling point, this is important because the vapor pressure, and once that reaches the atmospheric pressure, then it boils. So if the atmospheric pressure decreases, then the vapor pressure is going to decrease. All right, what would happen to carbon dioxide? We have here a phase diagram of carbon dioxide. Look at what it's asking. We're looking for carbon dioxide from negative 60. Negative 60 would be somewhere down here. And we're going to 30 degrees Celsius. 30 degrees Celsius, let's see, that's up here somewhere. All right. And what would happen, heated up from 30 degrees at 6 atmospheres of pressure. So 6 atmospheres of pressure is kind of up here somewhere. All right. So what happens if I do that? Well, the carbon dioxide is going to start over here as a solid. This is my solid phase, and this is my liquid phase, and this is my gas phase. So I'm going to go from a solid all the way through a liquid to a gas. So what I will see happening is I will see it melting, going from a solid to a liquid, and then eventually to a gas. What would happen at 0 degrees Celsius? Let's see, 0 degrees Celsius is right about here. If I increase the pressure from 2 atmospheres, well, 2 atmospheres probably is right about here. So I'm going to be right there. I'm going from 2 atmospheres, and I'm going to 60 atmospheres. 60 atmospheres is way up here somewhere, right? And I'm going up at this temperature, all right? So I start here, and I end here, and I'm going from a gaseous phase to a liquid phase. So that's what I would see. I would see it go from gas to liquid. In other words, I would see it condense. How about this one? What happens if I'm at 25 degrees Celsius? 25 degrees Celsius is right about here. And I'm decreasing the pressure from 80 atmospheres, way up there, all the way down to 1 atmosphere. All right, so here, this is a liquid phase, and this is a gaseous phase, so I would see it essentially boil. Right? The liquid would become a gas, so I would watch it boil. And finally, what would happen if I go from negative 80 to positive 80 at 1 atmosphere of pressure? Well, negative 80, let's see, negative 80 is going to be down here, and this is 1 atmosphere of pressure, and I'm going up to positive 80. Well, that's way off the scale. That's way up here, 80. All right, well, what am I doing? Well, I'm going directly from a solid, that's this kind of greenish phase over here. All right, I'm never going through my liquid phase, and I'm going directly to a gaseous phase. Right, so I go directly from a solid to a gas. I never went through the liquid phase. That is called sublimation. And that's what we see typically when we look at carbon dioxide. All right, what would happen if we increase from negative 60 to 20 at a pressure of 70 atmospheres? Well, 70 atmospheres is way up here. And I'm going from a temperature of negative 60, which is somewhere about here, to positive 20, which is somewhere around, let's say right about there, right? So I'm going from a solid to a liquid. Maybe I'm going barely to a gas. It's kind of hard to tell exactly where 20 would be. But anyway, I'm getting very close to becoming a gas. So I would definitely go from a solid to a liquid phase. All right, that's it, folks. Hopefully you can read a graph. If you have questions, please see one of us in class. We'll be happy to help you. Take care. See ya. Bye-bye.